Anyway, if anybody wants to play with it later. Okay.
Or combine them together. There's a dot matrix toaster to send data and then spectral analysis to read the data and then have a network.
Yeah, or a toaster that burns spectral images onto your toast. And you know exactly what you're eating.
Well, I mean, if you scan the chocolate and the toast gets a spectral image, then you'd have to compare against toast that someone else scans. You'd have to have a toast library.
Yeah, but if you memorize all these, right, then you know what to put on here. I don't know. All right, so knapsack problems. All right, it turns out there's a really straightforward algorithm to find the maximum value you can put in a bag of given capacity. So let's say capacity equals 25. And what we want to do is create a function, max val of n, which returns the most value you can get in a bag with capacity n. So my answer, what's the most value I can get out of a bag that holds 25 pounds, is just max val 25. But max val doesn't exist, so we need to write this. So let's look at this just for one particular case. How do we compute max val of 25? Well, we don't know necessarily that we should start with the most valuable item. We don't know which item to start with. But we know we have to start with some item, right? The first thing we're going to do is we're going to pick one item and put it in our bag. Unless we're just going to say, I don't want to put anything in my bag, in which case the value is 0. And we know we can't do any worse than 0. So let's put one item in our bag. Think of this as a procedure that can be done in one of 4 ways. We can either start by putting in a mouse or a drive or a phone or a laptop. All right, so can I just get rid of the phone since it's exactly the same value as the drive? Let me just X this one out because it'll simplify our analysis. Actually, drives are more useful than multiple phones, but whatever. So max value 25, there's 3 possibilities, 3 possible cases. Case 1, add a mouse. And let me put some symbols for these, M, D, and L. Okay, case 1, add a mouse. Let me make a table. So the first item we're adding is M. After we put a mouse in our bag, what's the value of everything that's in our bag? The current value. 5, because there's only one thing in our bag. It's a mouse, it's worth $5. What's the remaining capacity?
18.
We can put 18 more pounds worth of stuff in our bag. Because our bag started with a capacity of 25, the mouse weighs 7 pounds, our remaining capacity is 18. That's one possibility. Second possibility, add a drive. So we put in D, the drive has a value of 9, and it weighs 10 pounds, so our remaining capacity is 15. The third option is add a laptop. So we start with item L, it's worth $12, and it leaves us with a capacity of 1. Let me add one more column. what's the maximum possible value we can get out of that remaining capacity? If we start with a mouse, we've got 18 pounds of capacity left in our bag. Do we know what the maximum value is we can get out of that 18 pounds? We don't have a number, but we have an expression we can write. What can we write for the max val of 18 pounds? That was a hint. Max val of 18. Assuming we have this fictitious max val function, this is what it does. It tells us the most value we can get for a bag with a certain capacity. So if we've got 18 pounds left, the most value we can get out of those 18 pounds is max val 18. And the most we can get out of these remaining 15 pounds is max val 15. And for a laptop, we have 1 pound left, we can get max val 1. Well, now we can write an expression for maximum total value. If we begin with a mouse, the mouse is worth $5. The remaining capacity can get us max val $18. The total value of this bag is 5 plus max val 18. If we start with a drive, that gets us $9, leaves us 15 pounds, which will get us max val 15. And if we start with a laptop, that's worth $12, leaves us 1 pound of capacity, which will get us max val of $1. And those are the only 3 possibilities. We either start with a mouse, a drive, or a laptop. And in each case, this is the most money that we're going to end up with. So what's the most money we can get out of all of these 3 possible cases? It's just the largest of these. And that's exactly max val 25. So max val 25 is just the largest of those 3 calculations. So this is a particular example of calculating max val at this number, and to do this, we need to calculate max val at these 3 numbers. Do these calculations, find the largest of those 3 sums, that's the value of max val 25. And this is guaranteed to give us an answer, and it'll give us a best answer. Right? Logically, it makes sense, hopefully. And since every item has a weight bigger than 0, the remaining capacity is always smaller than the capacity we started with. So we always need to calculate max val for some value smaller than 25, or n in this case. So this will terminate eventually. We'll keep getting smaller and smaller capacities. All right, does that basic setup make sense? There's still some details to work out, but the basic strategy as an algorithm is this straightforward. All right, let me take this one step further. So we'll stick with our inventory, and let's say that we want to calculate, let's say we want to calculate max val of 18. So we're recursing now. All right, so we're going to have a first item. Current value. Remaining capacity. possible value from the remaining capacity. And a maximum total value. All right, first item is the mouse. Has a value of 5. We have 18 pounds capacity in our bag. If we put in a 7-pound mouse, we have 11 pounds left. Max val of 11, and so our maximum total value is 5 plus max val of 11. Drive, value of 9. It weighs 10 pounds, so that leaves us 8 pounds in our bag, from which we can extract max val 8 worth of value. So this is worth 9 plus max val of 8. And then we get to the laptop. So the laptop has a value of 12. It weighs 24 pounds, our bag holds 18 pounds. So this leaves us a capacity of -6. And the max value we can get from a bag that holds -6, we believe is max val of -6. And so the maximum total value we can get if we start with a laptop is 12 plus max val of -6. And then we take the largest of these. And clearly we got some kind of base case going on here. So what's the appropriate thing to do with this laptop? When we call max val of -6, what should we do? Should we return 0? That seems to work in most of what we've done so far. But if I return a 0 from this, this calculation will say if I put a laptop in my bag, I can get 12 plus 0 equals $12 of value. And I cannot get $12 out of an 18-pound bag by putting a laptop in. The laptop won't fit. So what you really need to do is, when you see that you've got a negative capacity, change that to a 0. Right? So our maximum total value is either the current value plus the max val of this, or if the capacity is less than or equal to 0, it's just 0. And if you don't do that, if you try to just return a 0 from max val, you get bogus numbers. It breaks your infinite recursion, so you do get an answer, but it's not the right answer necessarily. The kind of cool mathy way to do this, though, would be to have max val return -infinity when you have a negative capacity. And then this would be -infinity, and you're guaranteed it's not going to be the largest of all 3, and it's the same thing as setting it to 0. But we don't do -infinity in C, so. All right, that's all there is to the knapsack problem, the non-fractional knapsack problem. And this is guaranteed to get you an answer. But it's expensive time-wise, for the same reason that Fibonacci was expensive. Because to calculate max val of 25, we're going to have to calculate 18, 15, and 1. And to calculate 11, we're going to have to calculate some others. And to calculate 8, we're going to have to calculate some others. And we're going to recalculate the same values again and again and again. So this is a great setup for dynamic programming. We'll save the values in an array after we've calculated them. Before we do all of this, when we come into max val, we'll just check the array. And if it's got that number already calculated, we'll just read it from there and return. And then it becomes a very quick algorithm to run. All right, questions about this? All right, let's write some pseudocode. This is probably going to be PA5. Okay, I got to figure that out by Friday, but it'll probably be doing this version of the knapsack problem. You'll read an inventory file that has your items, weights, and values. and you want to write a function that can calculate max val for n recursively, and you'll have an option of including or not including dynamic programming, so you can compare speed of execution.
Do you give us the inventory file, or do we have to generate?
I'll give you a sample inventory file, but it should work for any inventory file in that format. So you'll need to make something that reads that in from a file and saves it in some kind of structure, probably just an array of structures, and then uses it appropriately. This doesn't feel quite as sneaky as some of the recursive stuff, because at least we're doing some sort of calculation. We do a few additions, but it doesn't seem like enough to necessarily give us the final answer, but it actually does. All right, pseudocode.
This wouldn't work at a limited item.
Correct. If you're limited in how much of each item you can take, you need to modify this. And
Dynamic programming is complex.
yeah, I don't think you can just tweak this by putting some limits in. I think it actually changes how you get to your optimal. And this kind of stuff, there's all kinds of computational theory. You can take a whole course on correctness of algorithms that digs into kind of the theory of proving that certain algorithms work. And you can prove that this works pretty easily. But some of them get really weird. So let's see. I don't know how much pseudocode versus C I want to write. I'll stick to pseudocode. So imagine you have some kind of inventory, right, which is an array. And it's going to have the following fields. So maybe it's got a name, it's got a weight, and it's got a value. So we can say inventory bracket 0 dot name. That's the name of the first item in the inventory. And this is what you're going to read in from a file. So beginning of your program, prompt for the name of the inventory file, or take it from the command line arguments, I haven't decided. But you get the name of the file, you open that file, and you just start reading in. So you read in, say, the name, the weight, and the value. You store them in the fields for inventory 0. You add 1 to your index, you read the next line, you store those, and so on. And somewhere this finishes, you hit the end of the file, and you have a number of items in your inventory. So in this case, that would be 4 if we had all 4 items. So that helps you go through your inventory array. All right, so max val of n. So we need to choose the first item to go into our bag. So we'll just run from 0 up to the number of items in our inventory minus 1. And my helpful comment here will be add inventory I to our bag. All right, so how do we do that? I don't know if I need this, but I'll call capacity. Set that equal to n. I don't need that. So n is the bag's capacity. All right, if I start with item I in my inventory, value that I can get out of this is the value of item I, which is something like inventory I dot value, plus whatever the max value is I can get from the remaining capacity. So plus max val of n minus inventory bracket I dot weight. That's the basic calculation. If you add item I to your bag, you get a value of inventory I dot value. Your capacity diminishes by inventory I dot weight, and max val tells you what the max value is you can get from that. We need to be careful. So let's check and make sure that the capacity of our bag is at least as big as the weight of this item. If n is bigger than or equal to the weight of that item, then we know that this item fits in our bag. So we can calculate the value we get if we start with that. Well, that's 90% of our work. That's calculating each of these things. The only piece that's left is we need to ultimately pick the largest of each of these things that we calculate. So how do we pick the largest of a set of calculations inside a loop? This is something we encounter again and again. And I suspect it's one of those things that's never really talked about. My goal is each time I go through this loop, I'm going to calculate a new number for value. And I want to remember what the largest value is that I ever come up with. Just keep the biggest one. So let's initialize this. Best value equals 0. And each time I calculate a value, I'll just say if value is bigger than best value, best value equals value. So that's just remembering the largest calculation that I've made. And at the end of my for loop, best value must be the largest of all those calculations. Just return that and you're done. It's really that simple. There's nothing really weird going on here other than the recursion, which you've done a number of times already. It's just put together in a very interesting way. So we run through all the first items you could put in, and for each one, take that item's value, add the max we can get from the remaining capacity. Remember the largest of all of those calculations, return that. That's the max value we get from n. And this will just recursively call itself and do the right thing. Do we need a base case? What's this going to do if I call it to try to calculate max val of 0? Will it get an answer, or will it continue down the rabbit hole?
Just return 0, right? Because your for loop wouldn't even run.
My for loop will still run through all the items in my inventory.
Oh, never mind.
But because of this if statement, if I call max val 0, n is 0, assuming there's no items with a weight of 0, right? This if statement's never going to be true, so I'm never going to make this recursive call to max val. Best value starts off at 0, I never execute this code, and so when I'm done, I'll just return the 0, which is what you would want. It should never get called with a negative, because it can only get called with a negative if this is negative, and this condition should prevent it. But if I happen to call it with a negative capacity, like negative 100, again, this if statement will never fire, and it'll just return 0. So our base case is actually kind of embedded in that if statement. So it's got a different feel from the other recursions that we've done, but it works just as well. All right, so that's your basic knapsack algorithm. How do we add dynamic programming to this? Pretty easily. So, right here in the very beginning, if save n is positive, just return save n, because that's the saved value. Otherwise, do all of this stuff, and then right before we return, save best value into our array at index n. And you just took it from a problem that will blow up to one that runs very quickly. Pretty doable? Cool. All right. Let's look at a different problem. And this may be the problem you end up working on, I haven't decided. So this is a rod cutting problem. So the idea here is you have a stock of metal with a certain length, and you have an inventory sheet of how much people will pay you for different lengths of this metal. And you only cut it in multiples of 1 inch. So 1 inch, 2 inch, 3 inch, and so on. And there's a pricing table, right, for how much these different lengths are worth. And so here's a sample inventory. So length and value. And let's say we have 8 inches of material. So a 1 inch piece is worth $1, a 2 inch piece is worth $5, 3 is worth 8, 4 is worth 9, 5 is worth 10, 6 and 7 inch pieces are both worth 17, and the whole uncut 8 inch piece is worth $20. And your question is, how should you cut this up and sell it to maximize how much money you get? If you don't cut it at all, and you just sell the whole 8 inches, you get $20. But if I cut it into a 6 inch piece and a 2 inch piece, I can get 17 plus 5, $22. If I cut it into 8 1 inch pieces, I'll get 8 times 1 is only $8. So again, how do we optimize the value that we get for this? What's the maximum value we can get from a rod of length n? And it structures almost exactly like the knapsack problem. Say what? And this is what's interesting. We can, for at least small cases, we can usually do this pretty efficiently as humans. really difficult to say exactly what the algorithm is that we're using. But we can look at it and we can kind of say, like, I'm not interested in that, I'm probably going to use this as part of it, and then we can whittle it down and more often than not actually come up with a best solution. But it's some kind of weird multi-things going on at the same time / intuition, gut feel kind of algorithm. It'd be really cool to understand that though, like how that works. So recursively, what's the maximum value we can get from a rod of length n? Well, first cut, if we cut 1 inch of material, that's worth $1, and remaining length is 7 inches, max remaining value is max val of 7, and total value, so it's 1 plus max val of 7. And if you start with a rod of length 2, you end up with the value of that, which is 5 plus max val of 6. And if you start with a rod of length 3, you get $8 plus max val of 5, and so on. And so you have 8 calculations to make, each of them involving a recursive call to max val. You take the largest of these, that's the value of max val n, or 8 in this case. So if your first cut is at 7 inches, you get $17 plus max val of 1. There's some symmetries in here, right? If you cut it into a 1 inch and a 7 inch piece, it should be the same as a 7 inch and a 1 inch piece. We're not really taking advantage of that in here. So this code looks almost exactly like that code, right? Our inventory is our value and length. We don't even need the length if we use the index smartly. And the value is just the value of rod that length plus max val of the current length minus the length of the cut that we just made. And so if you're only allowed to make certain cuts, in other words, if a 3 inch piece was worth nothing, right, it's the same algorithm. So what does this look like when it executes without dynamic programming? We want the max val from an 8 inch rod. It's going to have to calculate the max val of each of these smaller lengths. And to calculate max val of 7, it's going to have to do 6, 5, 4, 3, 2, 1, and 0. And to do 6, it's going to do 5, 4, 3, 2, 1, 0, and so on. And to do 6 here is going to do 5, 4. And this is just horrible, right? It's a very lopsided, very full tree. And you can see where dynamic programming is just going to lop off major sections of this tree, right? All of this stuff is going to disappear once we've done max val 6 once. All of that will go away. Now, in this case, we have the advantage of knowing that to find max val 8, we need to calculate max val 7, 6, 5, 4, 3, 2, and 1. And so we can actually turn this problem around and think of it from the bottom up. what's the maximum value we can get from a 1-inch piece of material? Put this one back to 8. So the maximum value for 1 inch is 1. No argument about that, right? Okay, what's the max value of 2? It's the largest of 2 possibilities. Make an initial cut of 1. So if we cut 1, we get a value of 1 plus max val of 1. Or we don't make an initial cut. We get $5 from our 2-inch piece and whatever we can get from a 0-inch piece, max val of 0. Well, we already know max val of 1 is 1, so this is equal to 2. And max val of 0, we always know that's 0. So this is 5. This is the most we can get. So we've just calculated max val of 2 is equal to 5. All right, what's the max val we get for 3? If we make a cut of 1 inch, it's 1 plus, I'm going to start doing MV for max val, 1 plus max val of 2. Or if we make a cut of 2 inches, it's 5 plus max val of 1. Or if we do a cut at 3 inches, it's 8 plus max val of 0. And we've already calculated these. This is our dynamic programming memory on the board. This is 5, this is 1, this is 0. So this is 6, 6, and 8. Here's our maximum value. And now there's no recursion, right? Because I know that when I calculate max value of 4, all my previous max values are already in my array. They're on my board. And I'll be able to use the 0, 1, 5, and 8 to find max value of 4. And I'll do this last one just to illustrate how easy it is. So 1 plus max val of 3, 5 plus max val of 2, 8 plus max val of 1, and 9 plus max val of 0. And this is 8, and this is 5, and this is 1, and this is 0. So there's 9, 10, 9, 9. Largest value is 10. Max val of 4 equals 10. And you just keep going. You do a little bit more work at each step, but it looks like order n squared, right? Because we had to do one calculation, 2, 3, 4, 5. Sum of integers roughly n squared. It's a whole lot better than like 2 to the n, which is where it's heading recursively. All right, so maximum value we can code up by filling in our values from 0 on up, or we can code it with an algorithm where we work down from max val 8 and do our recursive calls, and we can do that with or without dynamic programming. So there's 3 different ways to go about that. And what I may have you do is do all 3 and generate some timing information in addition to the code. See how those play out. So I'm still thinking about it. All right, questions on this? Is it just me, or is like 2 hours a long time to do data structures?
Yeah. Well, it's a matter of 2 classes a week versus 3 classes a week.
I don't know.
Did we do 5 last term?
Yeah, the other section is 5 days a week.
I know we covered a lot of this in 215. That's why I was kind of spacing
Yeah.
out for a lot of it, but.
Yeah, sometimes we do.
No, it's fine, I'm still something to wrap my head around.
Yeah. I don't think I'm doing this year at 215, but we have in the past. Any worries if you were to try to code this up, other than details, say calls and all that stuff? All right, cool. So,
Is this one we want to store? Like, when you're talking about what was the phrase to describe what we did earlier with Fibonacci, where after you find the max value of
dynamic programming.
dynamic programming?
Yeah, so you're definitely gonna wanna use that. You don't need it with this. I mean, effectively, you're using it with this. Yeah, you don't wanna just call recursively, because you get that big wide tree that goes sort of geometrically. So yeah, you wanna save your value, so that's what that green section of the algorithm was. Just to avoid that. So that part and that part, that's your dynamic programming.
Right.
So save at the end and check if it's saved before you start. And it basically brings you to the case where you're doing the same amount of work as if you start from one and work your way up. But dynamic programming is more general because if your inventory of weights didn't include certain lengths, right, you might not be able to just build up from one. But if you do it in sort of this demand-driven way where you want n and so you calculate the sub-values that you need, then it doesn't matter how the inventory is spaced out. Other questions or comments? All right, that's about all I have for dynamic programming. So I'm going to end this here, and Wednesday we'll either go into sorting and searching, or we'll talk about balanced trees, probably balanced trees, because it's something good to have seen, and then we can use it in 223. So we'll probably talk about tree balancing on Wednesday. All right, look for another quiz tomorrow online. Should open at 8 and be due in 24 hours, and probably another one Wednesday.